At this point, you should have already done part A and B. I'm just going to be going through it quite quickly. So here we've got mass M, this is 2M. We're drawing three-body diagrams for each of them. Of course, they both feel force of gravity, and the 2M is going to feel a greater force of gravity. Each of these is also going to feel a tension force pulling against or upwards. This is just one string, so it should be the same tension force. So actually, I should have decided the way it's going to accelerate. If I have a 2M here and an M here, hopefully you agree the 2M will win. It will accelerate this way, and the M will accelerate this way. So here, because I know this one is accelerating up, I know that the tension force, or the upward force, would be greater. This one will be accelerating down, so the gravity force is greater. And these two are the same tension force, right? Not the same force of gravity because they have different masses. Now we write our Atwood equation. So here, my net force, always do bigger minus smaller. In this case, accelerating up, tension minus force of gravity. The order absolutely matters. And then here, net force greater minus smaller would be Fg minus T. Now we're going to replace my net force is just mass times acceleration, T minus mg. Here, net force is still mass times acceleration. It is not ma, because this one has a mass of 2m. So this becomes 2ma equals, the force of gravity is mass times gravity. This guy has a mass of 2m, so this is 2mg minus t. We want to get we want to substitute in for t to get rid of it. So first I have to get t by itself, ma plus mg. This is 2ma, 2mg. We need to be careful when we subtract this. I get both terms subtracted. Now we're going to combine our like terms. So I'm going to add this ma over. 3ma plus ma, 2ma plus 3ma becomes, I don't think I said that right, whatever. 2mg minus mg becomes just 1mg. Trying to get a by itself, we're going to divide the 3m over. Here, I have an m on top and I have an m on bottom. This does cancel out right here, so this is just acceleration is g over 3, or you could say 1/3 g. It's the same thing. For part C. So before you actually solve for part C, I want you to think about if I were to add in, so I still have the m, I still have the 2m, now I'm adding in this mass 3m sitting on this table. It's frictionless, so I don't have to worry about friction. Compared to this situation, so compared to what we just did, do you think your acceleration will be more, less, or the same if you add in this 3m right here? So talk to your partner, more or less or the same acceleration. Alright, so what we're going to do is we're going to actually solve for acceleration, and then we'll see. So everyone should be drawing the three-body diagram for each of these. Now notice I have two different strings here, so I don't have just one tension anymore, so you're going to want to make up names. I called this string the tension in this first string, T1, and I called the tension in the second string, T2. So go ahead and use that to draw your three-body diagram, so pause while you were doing that. For here, so this guy's net force or free-body diagram hasn't changed much. It still has gravity. This one, it's still going to accelerate the same direction, right? This guy is pulling more than this guy is pulling down. So this guy goes down, he will go up, and this guy will accelerate to the right. So I drew my free-body diagrams with the forces showing that. So notice this guy is going to accelerate up. Here, I have a bigger force to the right, and then here, this one is going down, I have a bigger force down. I had two different tensions, so the tension pulling the M up was T1, the tension pulling the 2M up was T2, the tension pulling to the right on the 3M was T2, and on the left is T1. So everyone should be writing your net force equation. We have three net forces, so everyone do that, pause. Go ahead and check, make sure you have the same. Now we're going to be replacing everything that we can, so FNS and FGs, and make sure you're paying attention. This has mass M, this has 3M, this has 2M. So everybody go ahead and replace. Right, hopefully you agree with these substitutions. Now I am trying to get the acceleration by itself, so I have two variables that I need to get rid of. Everybody turn to your partner, tell your partner the two variables we need to get rid of. Hopefully you said T1 and T2, so I would get rid of T1 first. Tell your partner which equation is easiest to solve for T1 for. Hopefully you said the first equation, so everyone solve for T1, substitute in, so pause for just a minute while you do that. Alright, so we have substituted in for T1 into this second equation. Now it's 3MA equals T2 minus MG minus MA minus MG. I want to clean this up a little bit, so I can add this MA over. 3MA plus MA just becomes 4MA. And then I'm going to add the MG over as well, so now I have T2 solved for. Hopefully you're thinking, she probably did that so she can substitute in. I did. So I'm going to take T2 and I'm going to substitute in for T2. So you guys finish it off, solve for work A. So pause while you're working on that. Alright, here when we add over our 4MA, these are like terms, it becomes 6MA, 2MG minus MG leaves me with just 1MG. To get A by itself, divide this 6M over. Here my masses cancel out, so this is just G over 6 or 1/6G. So now what it's asking is, does this equation that we got make sense compared to what we got before? So earlier, we got the acceleration was just 1/3 G. Now with this 3M here, we're getting 1/6 G. So I want you to talk with your partner, why does this make sense? So hopefully you said something about less acceleration, right? 1/6 of G is definitely less than 1/3 of G. From the beginning, we should have said that this would be less acceleration. So there's a lot of ways to think about this. I thought about this as a whole system. So if you're thinking about the entire system, the forces that are causing it to move is this force of gravity, but then counteracted by this force of gravity. Which is why up here, right, we had on top we had the 2mg minus mg, this part, the 2mg minus mg. Here, I still got that. I still have the 2mg minus mg. The only difference now, I haven't added in any extra outside force. I haven't added to like my net force accelerating the system. The only thing I added is that now I have more mass to accelerate. So see how the 3m is just like extra, it's like dead weight, right? It's not actually helping pull it one way or the other, it's just more mass to be accelerated. So when we're thinking about these, we can kind of think about it as one whole system. The net force is going to be this force of gravity, but subtracted by this one. Here, I have the exact same net force acting on the system, but now instead of accelerating just the 3m, I have an extra 3m, so it's accelerating a total mass of 6m now. So here, how I explain this, you have the same net force. Now I'm putting net force acting on the system. So the reason I'm putting it in, what are those called? Quotation marks, is because when we're talking about a net force, normally you're talking about net force on the object, like F net for 1, 2, object 1, object 2, object 3. I'm talking about the net force on the system. So that would be this gravity minus this gravity. So I still have the exact same net force acting on the system, but now you have more mass to accelerate. So we're going to get less A. So if you think about your equation, A equals net force over m, right? If I'm keeping the same net force but I increase mass, then your acceleration will decrease because m and A have an indirect relationship. Definitely other ways to explain this. You could have said, talked about like the free body diagram of this guy. He still has the same net force, but it's going to have a greater tension because it's pulling more masses or more weights behind it. That means overall this guy has a smaller net force, which would have a smaller acceleration. I want you guys to at least understand the system explanation of it though. Alright, for number 1, I want everyone drawing your free body diagram for each of these and then writing your net force equation. So pause while you are doing that. Alright, so M1 is sitting on a surface, so I know that M1 has a force of gravity because it's not in outer space, but it also has a surface holding it up, so I have Fg and Fn balancing each other out for M1. Now M2 obviously has a force of gravity. It does not have a surface pulling or holding it up. It does have tension pulling it up. I need to decide which way this is going to accelerate. So this is totally frictionless. And I have something sitting on a frictionless surface and then being pulled by this weight. So no matter what these masses are, no matter if this was only 1 kilogram and this was 100, either way it's getting pulled and there's no force going against it because there's no friction. So this guy is going to accelerate sideways and M2 will accelerate down. Now I know for sure that when I draw this free body diagram, the Fg is greater, so the tension is not as big. That tension is the same tension pulling this one because it is the same rope or string, whatever it is. So I have tension pulling to the sideways. Again, frictionless, so I'm not taking into account friction. So I have force of gravity, and then the only other forces are forces that you have to be in contact with. That's the normal force holding it up, the surface holding it up, the string pulling it sideways, and this string pulling up. Now our net force equation is pretty easy. For the first one, it's tension. For the second one, it is Fg minus tension. Now you're going through and you are substituting anything you can and you are solving for the acceleration. So you guys work through this, pause. Alright, so for this one, we have tension, we replace the M1A, and then F net replace M2A, of course Fg is just M2G. We had tension solved for, so I substituted in. Here I had A in 2 parts, so I combined them, and then I factored out the A, and I divided that over. You've done this a lot, so hopefully you feel good about this. Now I want to talk about how this expression is different than what we were doing yesterday. So what we were talking about yesterday was when you have 2 hanging like this, and we got this expression, the difference between the masses times g over the total mass. Here, I still am dividing by the m1 plus m2, but I only have m2g on top. So everyone talk with your partner, why in this case, zoom out. Why in this case do I have subtraction, but in this case I only have the M2G? So talk with your partner real quick. similarities. So you should notice that both of them, you're dividing both masses, which makes sense because both masses are getting accelerated. What's different is what's on top. So here, only the m2g is accelerating it, because see how the gravity of this guy is getting canceled out by the normal force? So it's only this guy's weight that is accelerating it. Whereas here, this guy's weight was accelerating, but then this one was kind of counteracting, so you had to subtract their two weights, their two mg's. So let's go ahead and write that down. Now, only the force of gravity of m2 is helping to accelerate the system, because the force of gravity of m1 is not against the motion in this particular case. Whereas before, yesterday, when they were hanging side by side, right, they were kind of balancing each other out or subtracting, counteracting each other. Here, right, if I increase this mass, yes, I still have more mass, but it's not necessarily like a force against me. I still have more mass, right? I'm dividing by a greater mass, which would make a smaller acceleration, but I haven't changed like the net force on the system, which is just this force of gravity of m2. I want everyone to try 2 on your own. Pause while you're doing that. Here, I don't think I need to talk through it. Pretty straightforward. Draw your free body diagram, substitute in for t, combine like terms, you get 1/4 g. If you have questions, you can ask your partner. What I want us to talk about is number 3. So number 3 is a continuation of number 2, but now there is a coefficient of friction between the block and the table. So I want everyone redraw your free body diagrams for both of these and write your net force equation. Okay, so our free body diagram should look very similar. For this mass, I still have gravity pulling it down, I still have tension pulling it up. For the 3m on the table, still got gravity and normal of the table, right? And then I have tension pulling it to the right, but now it says there is friction between the table and that block. So I have friction opposing that motion, which in this case is going to the right. Now the reason I said that the friction force is smaller than the tension force is because it says that assume the blocks move when released. So if they're going to start to move, that means the tension force was greater because it's going to start to accelerate. It overcame the friction force. So then I know T must be bigger. Net force, and if you're like, why do you not have friction for this guy? Well, is this guy touching the table? No, so it shouldn't have any friction between it and the table because it's not touching the table. So his net force is still the same. This guy, instead of having a net force of tension, has a net force of tension minus force of friction. So now you are substituting, replacing anything that you can to solve for A now. So pause while you do that. So here, F net became MA, FG is MG minus tension. Oop, that's supposed to be F net equals a T minus FF. F net is 3MA, tension minus force of friction is just mu Fn. Now, Fn is not like a given, so I need to find what Fn is. So if we're looking at this guy, the normal force is equal to the force of gravity. And the 3m's force of gravity is just 3mg. So I can replace this for the normal force, so mu Fn is just 3mg. Of course, I'm going to get rid of my tension, so I'm going to get T by itself with this.